Okay, we're live now.
Mm.
Hello, everyone. Welcome to another virtual session. You are watching YouTube Live. We are from Java User Group Bangladesh. I'm Bazlur, your host. I'm from Dhaka. Where are you from? Later.
Hey, I'm Roberto, and I'm from Portugal.
Okay, great. And the audience, I would like to ask you as well, where are you from? Let us know in the comment section. So the comment section, the window you are watching this on the YouTube, there is a chat section. So I would like to ask you your questions there as well. Where are you from? So that we can get a context and you can make it interactive. Well, we have a special guest, Roberto Cortez, joining all the way from Portugal. Cortez, how are you doing, man?
I'm okay. Thank you so much for asking. It's a pleasure to be here with your JUG. Unfortunately, we're not able to do it physically, but at least we have technology that allow us to do these online things, which is great.
All right. Do you know that we have a huge number of football fans who root for Portugal in the World Cup?
Oh, thank you so much. I'm sorry to disappoint you, and we're not able to win it. But we got the Euro Cup, which was not that bad a couple of years ago.
Yeah. So fine. So let's go ahead. All right. So those who already joined earlier, you already know how we do this, and those who joined today, for those actually, we do virtual meetup bi-weekly. That is every other week, and we talk about Java. Well, not exactly Java. We talk about various topics, most relatedly to software development. So today we're going to talk about REST security. Well, we all know that how it is hard to secure the REST API. It has a huge, in fact, steep learning curve. So luckily we have Cortez today. He is going to uncover a lot of details and a lot of secrets for how we can secure the REST API. And let me introduce him first before going to this session. Well, he is a senior software engineer at Tomitribe. I'm sure everyone knows Tomitribe, so I don't need to say about it. He is a speaker. He's also a Java champion. He's a Java 1 Rockstar. And there is a conference called JNation. I'm sure many of you already know. He's a founder and organizer of that JNation. And most importantly, he's a JUG leader. Okay, so I'm sure he has a plenty of knowledge, ideas, and experience that we can get benefited from. So without further ado, let me give it over to Cortez.
Thank you so much. That was a wonderful introduction, and I think we met when I done a session with Bruno Souza about like speaker secrets, right? That's when you actually connected with me to do this session. And I mean, I'm here. I mean, I'm going to do the session. I'm here to help as well. So if you have any kind of other questions around communities or JUGs or conferences or everything else, I'm also happy to answer those in the end.
All right.
So yeah.
So I would like to ask the audience to if you have any questions related to anything. I mean, as Cortez said, he can answer. Let's say developer anything related. I guess Java. I mean, he can answer.
Yeah, probably. If you ask me questions about .NET, I'm not going to be able to answer them. But yeah, I mean, throw everything that you can at me, and I'll try to give my honest answer on everything.
All right. So let's go ahead on the topic that we are going to have today.
Yes. Thank you very much. So let me just share my screen, and let's go to the slides that I have prepared for you. So let's go and share, and now let's go and hit play. So I'll hopefully now seeing my slides, right?
Yes, we can see your slide now.
Yeah, it's full screen, right?
Yep, it's full screen.
Okay, wonderful. So yeah, thank you again for having me here, and welcome to the session about deconstructing REST security. So these sessions are a little bit interactive, which is probably going to be a little hard for me to do it when I'm doing these without an actual audience in front of me. So some of the things, some of the slides might look a little bit weird, but I'll try to go around them.
Okay.
Anyway, the concept of this session actually came out when we at our company, Tomitribe, we were rolling out Tommy, which is an application server based on Tomcat that supports Enterprise Edition Java. And we're rolling out the server to one of our customers. And basically, after we were done, he then came to us and asked us, okay, so we have all of these running. So how do we going to secure this? And at that time, we actually didn't have a proper answer. And we actually came to him and say, hey, maybe you can do it with Buzzy cost. And of course, that's not gonna cut it, right? So we went out and started investigating a little bit about security to be able to answer our clients' problems. So I'm going to skip this slide since I was already introduced. And anyway, you can keep my contact if you need them to reach me out later. So moving forward, we went out and started reading some of the security standards that were out there. And one curious thing happened was that we end up like starting in one of the spec, and then that spec referenced another spec. So you went out and read like 20 pages, and then you have to go out and read another 10 pages for another spec. And then that other spec references a third spec that you also went out and read. And in the end, sometimes we got locked into these circular references from spec referencing each one another, and it was a little confusing to us because this specification has a lot of options, and it was hard for us to find something to fix our specific problem. Another interesting thing that we found on the specs out there is they tend to rename old concepts into new terminology, and this causes you doubt and issues. And why? Because when you were seeing this new terminology, you actually think that's a new thing, and you're not sure what they're talking about, so you get confused. But that's actually not the case. When we study the things and we actually look into that, we ended up figuring out that some of these new terminology that the new specs or the new security standards are using are actually old concepts that they're just renamed into new stuff. So this talk in the end is a very opinionated and narrow approach to perform security for REST applications. So these are going to be our agenda for today. We're gonna start with basic auth, just to like do the introductory part, and then we're gonna talk, of course, of some of the most modern security approaches like JOT and auth 2, which are very popular these days. And these are the Google and Facebook style of doing security on their own APIs. We're going to look how these can affect the stateless or stateful architecture. And then we're also going to look into HTTP signatures, which is the Amazon EC2 style of API security. And in the end, we're actually going to see how we can use both of them to achieve a very secure and a very stateless architecture using both auth 2, JOT, and HTTP signatures. So through the application or for the presentation, I'm going to give several examples of how using a particular technology or using a particular security scheme is going to affect your architecture of your application. So let's start with the baseline. In here we have an application, regular application, and we have 1,000 users. And let's just assume that each user has like 3 devices and is going to send 1 request per device. So that means that each user is going to send a 3 request, and all the users are going to send 3,000 requests So we're going to call this TPS, for mean transactions per second. And now let's also assume that every time a user sends one of these transactions, these are going to be handled by our application, by our microservice application, and we require at least 4 hops on our application to handle that request. So that means each request is going to generate 4 hops on the microservice layer. And that, of course, means that we're going to generate 12K TPS on the backend. So this is going to be our baseline. So let's look a little bit into basic auth. So if you actually look into the basic auth message when you're sending in a request, you actually see, and this, of course, is the most secure mechanism ever that you ever find. No one ever broke this, right? You just pick up your username and you pick up your password, you separate it with a colon, and you basically foreign code it. I mean, it's super secure. Of course, this is not right? If someone is able to grab your message, they can easily grab your password, grab your login, just by looking into the header. And of course, this is very insecure. Okay, now if we apply the basic auth to our baseline architecture, usually when we have one of these, we end up having an LDAP or a database that we're going to authenticate these credentials against. So now let's imagine we're sending our 3K requests, and since we need to validate them, this also means we're going to have 3,000 requests or 3,000 TPS on our LDAP server or whatever other authentication server we are using. We also see that a lot of secrets are going to be sent over the wire. So all of these 3K requests or 3K TPS have the username and password in their own message. But how about the backend? Does anyone here secure the backend? Usually, the answers that I usually got when I'm doing this kind of presentation is a very small amount of people actually worries about the backend. They usually use techniques like IP whitelisting to do security, but that's not enough. So we think that since our backend is on our hands, that is secure and nobody's going to see it. But I mean, all of us have worked with consultants before, right? And they come into our organizations and they look into our code, they look into our architectures, they look into our systems, and then after a while, they move on and go do consulting somewhere else. But the issue is that they left with all this knowledge of our internal systems, and they can easily use it to gain access, or at least to know where it's most vulnerable, to attack it. So a good percentage of hacking and external hacks were actually inside jobs from people that knew the systems and knew how to attack them from outside, but knowing the internal from the inside. So this, of course, is not very safe. So the backend should also be secured. Also, now let's have a look into this additional improvement. So now we're going to secure each microservice, and that means we're going to use passing the username and password. So that means that we're going to send the password 12K times. So again, we are increasing the chance of someone actually grabbing our password because it's over the wire in a lot of messages. On the other hand, since each microservice is receiving the username and password, it needs to authenticate with the LDAP server as well. So now it means that our LDAP server is going to get hit by 15K TPS just to do authorization and authentication for that particular request. Now, if you think about it, LDAPs or even other authentication servers were not built to handle such a load. In fact, if you look at it on the entire load of the system, 15% of the system load is just the perform authentication. right? And it's not scalable. So that's why usually people end up using IP whitelisting. No, but if you look into IP whitelisting, it probably worked very well 5-10 years ago, but I believe that the IP whitelisting is not the solution anymore. And why? Because IP whitelisting is actually the enemy of elasticity. Now, with all these brand new systems that require you to do auto scaling and to create services to handle particular time loads, you cannot just go to your system admins and say, oh, I need you to go and authorize this IP for me, and then after a while do that again, so that they're just going to go crazy. I mean, of course, you can automate that, but that's not the proper solution. So the idea here is that you're not going to hard code a bunch of IP addresses in your network rules and routes between the servers, since on a cloud environment, you don't even know where things are running, or you don't even know the IPs where things are running. On the other hand, if you don't secure your microservice or your service in the backend, let's just say that one of the services is asking for Joe's salary information. Well, microservice A is asking that to microservice D, but D doesn't know who A is. So, okay, I can give you the information, but is this really secure? I mean, you can actually say, well, salary is not really that big of a deal. Well, for some organizations, yes, some organizations, no, but usually that's some kind of information they don't see posted online all the time. But what about if you're talking about social security numbers, or if you're talking about your health conditions, right? So you have to make sure that whatever information you're passing in on the back end, only authorized people can see it, or you're going to have a problem. Now, Latveria attacks. So this Latveria. Do you know where Latveria is in the world? So actually, if you look in the map, there's Latveria. Probably never heard about this country before, or maybe you have. So Latveria is actually a fictional country on the Marvel universe, and it's the country of Doctor Doom. Well, I have to come up with this country because, as you know, there are no bad countries in the world that actually hack people around. So only Doctor Doom does it. So now we have our architecture again, our baseline, and we have our healthy traffic, our users, and your free KTPS. And Doctor Doom decides to attack our system, and he's now sending 6 KTPS. And of course, we don't know which health is traffic or which one is actually bad. So we are going to have to authenticate them all. And that means that our LDAP server is going to be overburdened with 9 KTPS. So if Dr. Doom has enough resources, he can easily deny of service or application just by sending this kind of traffic to us and crash our LDAP or authentication server. Okay, so now let's look into other solutions. OAuth 2 is now something super popular, as we've seen before. It's something that Google or Facebook are using into their own APIs and even other popular applications. And there's actually 2 kinds of OAuth 2. So there is OAuth 2, I'm going to call it like regular OAuth 2, and then there is OAuth 2 post-JSON web tokens. So let's look at the first, and then let's look into how you will do it when you're using JSON web tokens. So when you have OAuth 2, it means that you're going to have a token that you're going to store per device. And each of the tokens is going to be different per device, right? So what that means is you log in, you get a token, and the token stored on whatever device you log in with it. So this means that you don't have to log you out. You can just revoke the token for a particular device. So let's just say that you lose your you'll use your mobile phone. So you can go and you can say that you want to revoke the token for that particular device. But the good thing about it is that since you log in, when you log in, you only have the token. No one has your password to log in with the token again, as long as you revoke it, or as long as the token lives. For instance, if you have a Twitter account, you can go to your settings and you'll see or even GitHub. So most of the modern applications have these options. You can go to the settings and you can see what your devices are logging in, and you can see the tokens, and you can revoke that for a particular token, and you'll be logged out just for that device. So now you can just revoke the device for an iPad, for a tablet, for a phone, for a desktop, doesn't matter. But the point is, you keep revoking tokens, and you don't have to basically change your password when you're being attacked, when you actually rob the password from your application or from your mobile devices. And what auth2 actually does is you first post the password to something called a password grant flow. And you do this using like a form URL encoded, and you pass in the login and password. And when you do this, you usually get the token. You get a refresh token. So the token is what you're going to send every time you want to interact with the system. And the refresh token is something that you're going to use to refresh your token when the token is no longer valid. So usually the token can be valid for like half an hour, an hour. Well, that's a policy of the API. They can actually live forever as well, but I usually don't recommend that because it's not really secure. If someone grabs your token and it's valid forever, only if you revoke it, then people cannot use it. But if you look into this, this is called auth2 password grant, but we're using a form URL encoding login, right? This looks exactly like we did this like 20 years ago. This is not a password grant. This is actually logging in. So this is one of the examples that I mentioned before, where some of the terminologies used and people heard about password grants on auth2, but that's actually just logging in. So now you're reading 30 pages on the auth2 spec, and they're calling this a password grant, but there's actually the same thing that we're doing for the last 20 years with logging in with a plain form. Now, if you look into the message, now we'll see that on the authorization header, we're just going to use a token, and we use it as we use the prefix bearer, so you can tell that we're using an auth2 token, and we send this in the request. So now we're not sending a login and password, just sending a token. So that means that our password is not really exposed on the wire. And of course, on every request that you're doing, you kept sending requests and kept sending the same token over and over. And every time you get a different response depending on what endpoints you're calling. So this is probably familiar with if you already done integrations with stuff like GitHub, Facebook, or Google. Now you do this for a while, and after a few minutes or even half an hour, boom, you get a 401. And that means that your token expires. So in that case, you usually go and do a refresh grant using the refresh token that you got when you logged in or when you actually do the password grant. So the refresh token will ask for a new token. The new token will bring a new refresh token, and you keep going. Now, the interesting thing here is when you're looking into the spec, the refresh token feature is actually optional. So that means that not every auth2 implementation out there supports refresh tokens. So that means that tokens, in some implementations, tokens never expire. And some others use the same refresh token over and over again. So there's a higher chance to get picked up. My point here is that refresh tokens should expire once they use, and when you request one or request a new token, you should always grab a new refresh token. So a refresh token should be one use only. So if this is not the case, if you're using auth2 and this is not the case, or if you're not sure, you should look into your implementation or look into your token server and see how they are doing things, because if someone, for instance, grabs your refresh token, if that refresh token is unique, and you use the same refresh token all the time to refresh your actual token, that's no safer than actually have the password over there, because people can just use it to grab a token and be logged in forever. So this is how it actually look like. So you have an old pair of access token, you grab a refresh token, then when you try to refresh it again, you get a new access token, a new refresh token, and you keep going and going and going like that. So now you can keep sending requests using this new access token until it expires, and then you have to request a new one. So this was actually, I believe, a little bit tricky and complicated. So what we have actually achieved with this, well, you have more passwords, or at least your devices have more passwords. For you, it's only a password, but this is kind of like having a different password per device. The point is, if someone grabs your token, it can still act as you. Now, imagine that you're sitting on your desk and you get a client call, and they come and say, "Hey, we have this security problem. We want you to fix it. We're using basic auth. We're using something that's insecure." You're not going to say to them, "Hey, here's a solution for you. You use more passwords." No, you say, "No, you're going to use tokens," right? So again, this is another one of those issues where the terminology is a little bit different, and that might confuse it. But in reality, what you have is a token. It's just like a different password all the time. So let's try to pick up a little bit of the terminology and try to use the names that we are more familiar with. So a password grant for me is actually logging in, and a token is actually a slightly less crappy password, since you were exchanging it all the time. Or you can just call it an equally crappy HTTP session ID, that instead of going on the URL or on the session, is just going on the authentication header. Okay, so now let's have a look into our baseline architecture again. Now let's just say that we require our users to authenticate at least one time to grab the token. So that means that they're gonna send their password 1K times, and then we're gonna still be sending the free KTPS with the token. Now our LDAP server, it's fine because it's not getting that many requests, because it just needs to verify the login and password when you log in, and after that the verification is done by the token server. So the token is stored into a token server, and that's when it's going to get verified. But now notice that the token server is now hit with free KTPS. So at the moment, we just introduce here a new component on your architecture. So we are complicating this a little bit. We have more requests on the architecture as a whole. And then we might have some problems with big data, right? Because every time you create a token, you have to store it in the token store. So when you authenticate, you can see it that user is valid. And if we want to start doing things like logging the users that were not logging in, but basically log the users that done several actions, you cannot get rid of the old tokens because the token is the one that's actually going to tell you who the user is. So the token store is something that you cannot delete. You have to keep it forever. So after a while, it might be only a few years, depending on what the traffic of your system is, but you might end up with millions of tokens. They're not being used anymore, but you still have to have them to reference all data in the past to basically know who was doing whatever action in the system. Well, at least if you look into our microservice architecture, you can at least propagate the token for all the microservices, right? So you don't really have to log them in. But there's still an issue. So what the microservice actually get is just like something that he cannot really comprehend. So microservice A again grabs the token, even if it's valid. He doesn't know who it is, so microservice A sends the token to microservice Z and say, "Hey man, I have no idea who this guy is, so we have to go and ask the token server to see if we can actually access my information." So now you're gonna have all the microservices going to the token store, and you're gonna do 12K TPS to actually grab the user information, so you know who it is. And of course, if you have 12K TPS and 3K TPS from the token checks, we're going to have 15K TPS, and the token server is just going to crash and burn because it's handling now 55% of the traffic of our system. It's just going to blow up. And in the end, we're going to be at 0 TPS. So again, this is not really scalable. And why is not scalable? Because we still have a fully stateful architecture. The clients, which are the users on our devices, are holding a pointer to a store, and the backend is also holding a pointer to a store. So every time that we need to retrieve user information, we have to query the token store to grab that information. But doesn't this sound familiar to you? You have a pointer and you have a store, and you use that pointer to grab an information on the store. Well, wouldn't this better to be called an access pointer, or better yet, an access primary key? This is not really different of having a table, which, well, doesn't matter how the data is laid down on the token server, but think about this as a table where you have a primary key that you give away to your users, which is actually changing all the time, and then they can use it to actually grab their information. So in reality, what auth 2 really means is it is a high-frequency password exchange algorithm, right? That's what it is. You just use your original credentials, you grab a token, the token lives for a while, and then you grab a new token, and basically the token replaces your password every time you want to interact with your system. So, and it's changing all the time. So that's why I call it like this. Okay, so before moving forward, and let's see how we can fix this, I want to introduce you to a general problem of a typical computer science problem, which is how do you detect that the file content or contents of a file have changed? So maybe some of you may say we can check the timestamp, or others may say you can check the size, or maybe you have to check both, right? So if you check the timestamp, check the size, and then check both. Well, I mean, but does that really mean that the contents change? Well, not really. So the actual answer for it when you want to detect these changes is we hash the file. So now we're going to talk a little bit about hashing and signing symmetric and asymmetric data. So about hashing. So hash is just a summarized data that you do, which is a magical statistical unique number that summarize a particular big piece of data. So statistically, if you're hashing like a 1 gig file, you can generate like just a unique number that's going to represent that 1 gig file data. For instance, if you look into GitHub commits, they use an hash, and Bitcoin also use hashes. Now, if you try to find an hash that is the same on all GitHub commits, you're not going to be able to find it. So this is actually magic. So, but it's not right. It's just math, but it does seem like magic. So let's give an example. So imagine like a snow globe. And in this snow globe, you have 250 flakes, and which represent bits. So now imagine that the stream of data is going for the globe, and now we're just going to shake the globe, and then we're going to stop it and shake the flakes. So it looks something like this. You keep shaking, 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 and after you're done, you stop the shake, you crack the globe open, and you pick up the flakes, and that's your hash. Of course, now hashes can be weaker or stronger. So we have a SHA-1, which is 128 bit hash that we actually stopped using because it's not secure anymore. So now we are using 256, and eventually we'll move to 512. And the point here is at some point in time, the computer power will be so big that you're able to compute super easily all the SHA, for instance, for SHA-128, you can compute them very easily. So it's easier to do it. So you keep moving and you keep increasing number of bits to make it harder. So it's kind of like a never-ending race. So each time the computer power catch up, you have to move you have to increase the bits to do the hashing. Now, the snow globe, just to give you a first example, but the issue with the globe is it doesn't sound deterministic, because when you're hashing the same data, the bits that you get of the hash, they're always the same. So now let's imagine a keyboard or a piano. So each time you play a key, that piano key is going to represent the bit. And when we press the key, we toggle the bit. So we press the key one time, it's going to be 1. We press it again, it's going to be 0. So let's going to imagine that we're going to play the data as it was a music. So we're going to hit the keys, and we're going to toggle bits 1 to 0 as the data is going through, like a music chart. When the data is over, we'll just stop the piano and we'll see what's the end result. Now, if you look into this, if someone changes the data that's going for the piano, you're also going to change the notes, because you're not going to play the same notes. So we're going to press different keys, and the hash is going to be different, right? But am I able to pick up the hash and generate the original data? No, because I only have, for instance, in this case, I only have 256 bits. I'm not able to from the hash to generate the reconstruct the original music. So now this is the hash, which is also known as a fingerprint. So it's a fingerprint of the data going from the piano. So now I have here a small example that everyone can do this at home, which is you can pick up like multiple like you can pick up like a file content, you can add some content into it, and then you can try to hash it. So in this case, I have an example of, say, Spain beats Croatia 6-0, and then you hash it, and these are the results you get. Now, if you pick up the file and you say Spain beats Croatia 6-5, the hashes are going to be different. So I'm going to go return to the one before. Now you see that the hashes, so Spain beats Croatia is the content of the file, and this is the other, and you see, of course, that the hashes are different. Now think about this. So of course I'm talking about a game, and we have a referee that has the final game. So he picks it up, he records on the file. Now the other, because Spain beats Croatia with that result, now the other team is unhappy and wants to change the score. So they send in a new file, and we can see that they change it. But how can we tell who is right? So because now we have a person that's saying that the result was one thing, and we have another one that's saying the result is another thing. So for instance, Bitcoin solved this issue by popularity, so the majority wins. If you have more people saying that that's the right hash, that's the one that's going to win. I'm pretty sure that you don't want to use this approach on our systems, right? Now let's imagine a bunch of hackers just piling up together and saying that their hash is actually the winning one. Of course, probably don't want to do that. So that's when you have the asymmetric signing. So you want to protect the hash. The idea here is that you use a symmetric. You can use a symmetric key, so both sides can read and write the hash, or you can use a symmetric key, so only one side can write and the other one can read. Now, here is just symmetric, so each one share a key, and with that key, you can lock in the data, and everyone can read and write it. So myself, I can just write a file and write the content, and someone else can open it up, read it, and then can write it again. So there is no security, or no. Well, I mean, there is security over here. At least we know that only these people could do it, but someone can actually change my content, and they don't know who's actually right, if it was me or the other person. Now, with an asymmetric key, that's not the case. Now, if we pick our example of a match, you have the referee, right? So the referee has an asymmetric key that's going to use to lock the result. Let's just say, again, Spain beat Croatia by 6-0. You're going to lock that result, and it's going to give a public key to each people that's on the stadium or everyone that's around the world, so they can use that public key to open up the result and actually see it. But no one's going to have the authority to actually change it. So they know that that result is valid because that was the one that the referee uses to lock it. Now, if someone else tries to come with a different result, their public key is not going to be able to open that result, so they know that that's not the valid one. So this is actually a way to distribute read-only data. Everyone has a read key, then you can check the score, but only one person can actually write it. So how many areas, for instance, let's just say, how many keys does, for instance, user needs to sign 1 million documents? They only need one. So because the key represents the authority, not the data. Okay. So let's go back to our auth tool now with JSON Web Tokens. So let's see how these concepts can change auth dramatically. So a JSON Web Token is actually pronounced a JOT, which is kind of weird, but that's how it is. So, and a JOT is nothing more than a fancy JSON map. where you can place whatever information you want over there, is base64 with all encoded and is digitally signed with a SHA key or SA key, and we'll see why. And inside it also has a built-in expiration. So that's how a JSON web token looks like. For instance, scopes, they're actually roles. So on the spec, there are also a couple of things that you can use to represent particular or standard pieces of data. Now, if you use a JSON web token instead of the regular token that we were seeing before, now we have a header, which has the algorithm that was used and the type, and we have the payload, which is basically a map of where we want to put into it, and which basically can be the token type, the username, the roles, and you can have an address, doesn't really matter. And you have a signature, which actually is made exclusively by the token endpoint when you request it. So if we pick up the concepts about hashing and signing that we've seen before, you can actually sign your JSON web token to know that token was actually generated by your token server and no one else. So if you look our token now as it was before, it was looking something like this, and our access token now with the JOT is going to look something like this, right? And of course, we want to use the smaller one, right? Because small is always better. Well, maybe not. This has a subtle but high impact architectural change. So what we had before was we have an LDAP. We pull the user info from the LDAP. We generate an access token, which is a pointer. We insert the pointer and the user information into the database. We send the access token pointer to the client, and the client holds the pointer and the server holds the state. So with JOT, what we can do is, again, we pull the user information from the LDAP. We format the data as JSON. We sign the JSON with a asymmetric key. We insert only the pointer into the database, and this is only for revocation purposes. And then we can actually send the actual token, which is the state, to the client. And now our server only holds the pointer and the client holds the state. So we actually reverse the concept. So if you think about auth2 with access keys, you're using an HTTP session, which is stateful, and auth2 with a JOT is kind of like having an HTTP cookie, a signed HTTP cookie, but it's completely stateless. Now let's go and see again our password grant flow that works exactly the same. It's called the password grant. You pass in login and password, and now you're just going to get a much bigger access and refresh token, which holds all the information that you require for the user. Sending in a message exactly the same. You send it as an authorization header as a better, and then you send the entire token. Now notice that since the token is signed, you can actually verify it. Let's have a look into our baseline. So we have exactly the same as we had before. We sent in 1,000 passwords to do the login, so that's fine for LDAP. The user still sending the free KTPS, but now remember our token is signed, and this can easily be checked by verifying the token with our public key. So if we know that the token was not signed by the private key that we expect, we can just reject that request immediately, and we don't even have to do any other call. So this is just CPU and memory in place. It's a very fast check, and the public key is super small, so we can actually cache it So that means that, or usually, or token store is going to get hit 0.55 TPS, and that only happens when we actually had to hit the refresh with a 30 minutes expiration. And so what's the impact of this on the backend? Now, if I have microservice A and say, hey, give me all of gallery sellers information, well, microservice D has the JOT. If you don't pass the JOT, microservice D can just say, deny the request, say, hey, not a chance, I'm not going to give you that. Now, if we pass in the token and we say, hey, give me Joe Sal's information again, microservice D grabs the public key, validates the JOT if valid. It can even check any roles that are stored in the JSON web token to see if the user can actually access that information. And if everything is good and valid, it can just return the result to microservice A. But the cool thing about this is he's doing all of this work without any additional request. Now, of course, Latveri attacked again. So Dr. Doom and his minions return to attack our system. And he's mad than ever. So now he was able to grab a few more boxes and now hitting us with 12K TPS. But if we look into our system now, there is not much problem when he's doing this, because we can easily discard all of his traffic by just doing the key check. The chances for him to actually denial of service of our application, it's we reduce that dramatically. I mean, we didn't remove it completely, because if you have a huge amount of machinery, you can actually saturate our CPUs that are doing the token check. But still, it's going to need a huge amount of CPUs to be able to deny services on this case. But on our end also, CPUs are super easy to scale. So this ends up to being an architecture which is truly stateless, and that we can scale way more easly, and we don't have to worry about having token stores or having LDAP servers getting hit and slammed with huge amounts of data, because what we're doing over here is we're actually passing in all the data to the clients, and we're just using the key to actually validate that the data was sent by us, and everything else we're just going to reject. Now, there's still one thing that I want to talk to you about. So there's still a little piece missing, which is I can still have the token and I can send it, but that doesn't mean that it's the right one. I can still have a valid token, but that doesn't mean that it's Roberto that's calling that service. It might be some hacker that just got my token. It's calling the service. So for that matter, there is something called HTTP signatures, and this is what we call the Amazon EC2 style API security. So for HTTP signatures, secrets never hit the wire. We sign the message itself to prove identity and to prevent the message tampering. There is a spec for this as well, which is extremely simple and uses symmetric and asymmetric signatures. This does not eliminate benefits of a JOT, but the idea here is you use this for no repudiation cases. So every time, if you're, I'm not sure if anyone on the audience ever used the EC2 API, but of course they have an API that allows you to request for, let's just say, 100 EC2 instances. So they make you sign the request. So they want to make sure that they can prove that it was you that did the request for that amount of machines that you did and not someone else. Because if you didn't do that, you can just say, hey, I didn't request for these boxes, you are wrong. And they have no way to prove it. But by making you sign the request, kind of like you're signing a contract when you call their APIs. And then they can basically say, No, you use your key to sign the request, so it was you. Of course, if you give the key to someone else and someone else that does something with that, I mean, tough luck. It's kind of like giving away your password to your passwords or even your passport to someone else. Now, signing the key is super easy. You take the full HTTP message and you can select some of the parts you want to protect. So you don't have to use the full message. So usually what you want to protect are stuff like the endpoint you're calling, the host, the date timestamp, and the content length. So with this, you can create what we call a signing string, since the method that you call doesn't really have a header name. There is this request target main app name to fill in that void. But anyway, you pick up this data and then you sign this string and you have this hash back. So now you can pick up this hash, you can encrypt the hash, and then you can use a signature authentication where you pass in what's the key ID that you use, what does the algorithm use, what were the headers that you use to generate the signature. And when you're sending the signed message, you will just send a request like this. So what's going to happen is on the other side, they also are going to have the key, and they're going to look into the request. They're going to look into the headers that you said you signed. They're going to use the headers that are on the request. They're going to try to sign them as well, and they're going to try to match it with the signature. And if, of course, everything is equals and it's the same, that means it was you that sent that message. Now, if something is different, that means that someone tampered with the message. They might have tampered the payload. They might have tampered the timestamp point that we're calling. And in that case, we're just going to reject the message. So the interesting thing about this is that now each of your devices or every time you're calling, you have a key. And there are no passwords that are being sent over the wire, because you use the key to sign the message or the payload, and then that's what you send. There is nothing going on over here. And this is basically using a signature auth with the previous baseline that we're introducing again with an LDAP and again with the 12K TPS over there. But at least on the client side, there is no TPS happening. Now, if you apply this same concept of the backend, it's exactly the same. Each microservice has the key, which they can use to verify that. So now, when microservice A asks, "Hey, I want to give Joe salary," you say, "Hey, Larry, sure, but why, Larry? I mean, we don't. I mean, the keys, they don't have the information of the user. They only tell us that the message is valid or that no one's tampering with." So that's when we get up with something called the auth2 proof of possession. And the auth2 proof of possession is actually combining both of these concepts that we discussed before, which is auth2 and JOT, with an HTTP signature. Now, think about the JOT as a password, as your password that you use on the airport, but it doesn't have a picture. So it says all of your information, but you cannot say it's you, because if you don't have a picture, you cannot. How do you tell that it's actually you, or even your fingerprint? Now, a signature is adding that picture or that fingerprint to your passport, and that proves that not the JOT is your information, and the key and the sign proves that that information is valid and it's actually you that's sending it. Now, the access token will look something like this. So we're not going to change it that dramatically. We're just going to modify it. And we're going to say that token type is a proof of concept. And we're going to say the kid over there, it's going to say that it's the key ID that we use to sign our token. Because we can have multiple keys to do it. So you can actually pick a different key every time you send a request. So the password grant flow is exactly the same. You get the access token, you get the refresh token, you log in with your credentials, but you now get the key that you're going to use to sign each request that you send. Again, you have one key, but it can be multiple keys, so you can use multiple keys to sign. Now, the JSON web token is going to look something like this. So this is an example of the key, the JSON web key. And if you decode it, it just looks like that. Now, every time that you want now to call a request, you're going to use the same JSON web token that you had before, but you're also going to combine it with the key. So now you send the authorization header, you pass in the signature, as we've seen before. Of course, now you cannot have multiple value. Well, you can, but you don't do it. But now you send in the authorization header of the better as its own header name, which is better, so the token goes over there. Now we're sending both the access token and the signature. Both can be checked by our system. And we sign the date to make sure that the signature is different every time, right? Because if we're signing, if you just sign the content length, the host, and the payload and the method that you're calling, there might be the same. So and then we're not sure if the request is changed or if it's done something else. Now, finally, and I'm almost, I'm like 2 minutes over, but I only have like 3 slides left. Is it fine? Can I just finish?
Yeah, go ahead. No problem.
Sorry about that.
No problem. What?
Yeah, so now we have our architecture, which is OAuth 2, JOT, and signature, right? So each of our JOT is signed. We're sending the free KTPS again. We do the signature and the token verification and validation. Our refresh token it hit the exact same thing. And we also do the signature validation and verification on our microservices. So we validate both the JOT and the signatures. And we can rotate the keys every time we do a refresh token when the token expires. So with this, now you can not only prove your data, but you can also prove that you possess the data. So that's what you call the proof of possession. So this is one of the newest security spec on the REST world. I mean, I don't know. I think it's like it came up like 1.5 or 2 years ago, but it's like the newest one, or the most recent one, so to say. So this is a specification. I believe it's still in draft, but I believe it's still going to see a lot of the REST APIs to implement this style of authorization, because I mean now you can think about as a double factor authentication on your REST API, and it's going to make them more secure and making sure that you're actually the person that's calling the service by signing the request by your own key and then passing in the token. So even if someone grabs the token because they don't have the key to sign the message, they're not going to be able to use your token for something else. So a couple of just observations is HTTP Signals is a very friendly approach. They don't solve the identity to load problem. So OAuth 2 and JOT, they improve this intrusion detection and prevention way easily. Plain OAuth 2 is not enough. They have issues with HTTP session-like implications that when you had before. If someone is able to grab your token, like before they could grab your session, they could still impersonate you. Well, in OAuth 2 with JOT, it's kind of like a signed cookie. So think about that in that way. And if you think about using this signed cookie with an HTTP signature, you end up having a more secure system. So this pretty much concludes my presentation. So I would like to thank you for attending this presentation. Sorry, I actually have like a typo here. It should be Chantar X. It was the last time I do a presentation for this group. That should be JUGBD. So sorry about that. Forgot to change it. But anyway, the slides and resources, you can find them. You can find this presentation on this website, drivesync.io, on the slides menu. If you want to see the presentation and get the slides back, you can see them over there. So thank you so much for being here with me and attending to my session. I hope that this was useful for you. And now I'm really open to questions if there are any. I'll be happy to answer them. So let me just get out of screen share.
Thank you. Really, it was a really great session. I'm sure it has a lot of content. I mean, it needs a lot, needs time to process. But I'm gonna watch this session again, and I'm sure it was really helpful, and I enjoyed it. I learned a lot of things from your presentation. In fact, I will probably have more questions to you. I guess I will have to ask them later, but I guess we have a few questions. I can take maybe one or two, perhaps, since we are out of time. Okay. So, so one question is, it's related to the web app. I guess you have the earlier slide. You have shown the token storing things in the, let's say, device. Or so he asked about that. Why do we keep the response token for web app in the cookies or the local storage?
When basically where you're passing in the token, you mean?
Right.
So the token actually goes on the other, right? So you can store it wherever you want on the application. So you can use I've seen it use it on the local token store of the browser, or you can store it as a cookie. So there's at this point there is really no, as far as I know, there is really no convention over there. On the client side, you can just store it wherever you want, as long as then you're able to retrieve it to use it again when you have to do the next call to the app. Does that answer the question?
I guess that's answered the questions, and I guess we have few questions, but I'm sure those are already answered from your slides. So let's not repeat that. And thank you again for your time, and we really learned a lot of things. And in fact, audience also thank you. We have learned a lot.
Okay. Wonderful. So, I mean, if there are any more questions, please, you can reach me out on Twitter or my email, and I'll be happy to answer that as well. So again, thank you for the audience. I'm actually trying to find the YouTube link, which is right over here. So I'm just gonna join really quickly, and I'm gonna send something. Oh, I'm enrolling as my own JUG, so what doesn't matter. So I'm just gonna say thank you to all.
Okay.
Here on the chat.
Yeah.
And thank you for having me here. So.
Yeah. Thank you, Cortez, for this time and effort, and it's really helpful. So thank you.
Okay.
It's actually 11:40 here, so it's late almost.
Yeah. Sorry about that. I got a little bit excited and.
No problem. That's totally all right. It happens. I mean, we usually if in fact we go up to 12 sometimes, so that's usual. No problem.
Okay.
All right. So okay, thank you, Cortez, again for your time. We'll see you. And if we have any more questions from me or the audience, I'll definitely reach you and let you know.
Okay, very well. Thank you very much.
All right.
See you next time.
All right.
Bye-bye.
Bye-bye.